Alright, hi. In this video, we're going to be looking at stacks. I'm only going to be looking at kind of implementing stacks. So, I'm going to talk a little bit about a stack as an abstract data type, okay? And we're going to kind of work you through that. So we actually have a class hierarchy in this this video example. So we'll have an abstract base class for our stack. And then we'll look at implementing an actual implementation as an array and as a linked list. All right. So let's see. Before I get into kind of looking at some of the code and looking at our idea of the abstract operations the stack can do, I expect everybody intuitively knows what we mean by stack, right? At least a stack as you have run across them in the real world for real world objects. So you've stacked up stuff before, and that has the basic idea. So you created like a stack of books, or maybe like you put the dishes away and you have a stack of dishes in your cabinets, for example, right? A stack is defined as a collection of homogeneous objects. So it's a collection of objects all the same type. So in the real world, you might have stacked objects of different kind together, but it's more often the case that you usually do stack things that are kind of the same type. So stack boxes on top of each other, or stack your dishes in the cabinet. Okay. So usually for a stack, what you're doing is you're only putting items and taking off items from one end of it, right? So like a stack of dishes, it's especially if all your dishes are all the same, it's too inconvenient to try to take a dish from the middle or the bottom if you need a dish to make a meal with or to eat a meal with, right? So whenever you unload the dishwasher, you just put them on top. So that's known as pushing your items on top of the stack. And whenever you want a new item from your stack to use it, you pop an item. You take the item from your stack, all right? So in the example code that I have for this week, I didn't split the things into different files. Normally, this code would have been better if we had separate files for the header files and CPP files for the implementation for each one of the classes that I have in here, but I have quite a few of them, and they're all relatively small. So instead of a bunch of files, I put them all into the same file here. So let's first of all talk about a stack as an abstract data type. So our textbook uses that term, and it's common in when we talk about data structures, and it's common in programming and software engineering to talk about abstract data types, right? So what we mean by that is we just mean what are the operations that kind of define what it means to use a data structure. So what are the definitions of the things that you can do with a data structure of some type, all right? So for a stack, I already mentioned them. The most basic, and these vary a little bit. So you can look at different implementations, and they might have slightly different variations on the things you can do to a stack that define the abstract type of a stack, right? So I'm going to use not all the ones that our textbook used, and some of these I changed a little bit the name from what our textbook used. So I'm going to define these as our basic operations for a stack. So if you have a stack, let me go down to some of the more canonical ones first here. If you have a stack, you can push an item onto it. Okay, so the push function takes some new item of type T, okay? And in the implementation for pretty much in C++, when you're implementing an abstract data type, you're gonna define a template class of the thing so you can have stacks of any type that you need, right? So we use template classes for our stack abstract data type. So we can make stacks of ints or stacks of doubles or stacks of strings or whatever we want. Okay. So the things you can do with a stack is you can push a new item onto it. So when I push a new item, the item it goes to the top of the stack. I can look at the top of the top item. So this is kind of more. This is like peeking at the type item. So if you ask for the top item, it returns the item of type T that's on the top. Okay. In this abstract data type definition, top and pop are different operations. So in some definitions of a stack, you might see top and pop combined as a single operation. So here, the way I'm using them, and the reason why I do this is because this is the way they're done in the C++ standard template library that we'll talk about at some point in this class. So, but you can imagine a single operation called pop top that would both return the top item and at the same time remove it. Okay, but in our case, there's two separate things. If you look at the top item, it's still on the stack. You're just peeking at what the top item is, and so that you can use it. If you want to actually remove it, you need to do a pop. That's known as popping the top of the stack. So pop actually removes that item, so it's no longer on top of the stack. So whatever was the next item on the stack now becomes the top item if you pop from the stack. And then some other things you can do with stacks that are, useful, but not as used often. There's a method to determine whether the stack is empty or not. This is mostly used for this type of ADT specification of a stack because it's undefined what happens if you call top or pop on an empty stack. So if you try to pop an empty stack when there's no item on there, it's really not defined. So most implementations throw an exception, or they might just crash, or your program might halt if you try to pop from an empty stack, right? So the only way you can avoid that is you have some way to query your stacks and determine if they're empty or not before you pop from them, or before you look at the top item. So that's what isEmpty is for, right? And then the only other kind of operation I define for our abstract data type, stack data type, is the clear operation, which if you have a stack and has some items on it, you can call clear, and it just empties the stack out, and it goes back to the stack being empty. Okay, that's what clear does. I think the book called it something different. I think it called it initialized stack or something like that, and I didn't like it because it's not really initializing it; it's clearing it or empty. So maybe another better name for this would be to empty or empty stack, to empty it out, right? So besides that, I also declare that all stacks have to support a toString method. So notice I talked a little bit about this when we talked about inheritance. Okay, so all of these methods in our base class for the stack abstract data type are pure virtual methods. So if I build a child class that inherits from the stack base class, they have to implement these methods. They have to implement clear, isEmpty, push, top, and pop in toString because they are all virtual, and they all have this equal 0, which means that they're pure virtual functions. So C++ won't allow you to declare a child class of stack without implementing all of these. All right? And in essence, when you're declaring an abstract data type, these pure virtual methods are the things that are the essence of your abstract data type. So they really define the abstraction of what it means to be a stack. Okay, and so an abstract data type is just what it means to be a stack. So we can make concrete implementations of our stack. And in this video, we're going to make two concrete implementations. One an array-based implementation, and one a linked list-based implementation. Okay. So yeah, and we define a friend function that overloads the output stream operator, but the output stream operator uses the toString method for the stack, right? So because, again, I talked about this in the later video, in the previous video when we talked about inheritance. But because toString is defined as a pure virtual function, this will do the right thing and call toString on your actual concrete implementations. Okay, so we'll see how that works here. So let's look at our first implementation. I'll come back to the empty stack exception here. So I'll first talk about implementing a stack using an array-based implementation. All right. So for this, maybe I should have drawn a picture, but this is pretty similar to examples we've had before. This is like our list types that we've done in a couple of previous videos. Okay. But here, what we want, of course, is we want to be able to push items onto the stack and pop them off from the top. And we're going to do this in our first one, keeping a block of items, so an array of items in memory that we can use to push and pop items onto. Okay. So our concrete implementation of our stack that uses array implementations, I call it a stack. This is the same as our supplemental textbook has an array and a linked list implementation, as does our primary textbook, but it calls it something different here. But I like a stack. So this is, notice this is an implementation of the stack abstract data type. But here we're implementing all those methods, clear, empty, push, pop, and top, but we're actually implementing them in this implementation. So we actually have to provide code for all these methods, as well as we also have constructors for our class here. So to do an array-based implementation, we need to keep track of, we need an array of items. And I'm going to show you an implementation here where we use dynamic memory allocation. So in this is different from our textbook, our primary textbook's implementation that has a maximum size. So in my implementation, if you push more items than you currently have enough memory allocated for, it will automatically grow the stack for you so by doubling its size. All right. So I'll show you how it does that. So, but in order to do this, we have to keep track of the top of the amount of memory we currently have allocated. So our alloc size. And then we just keep track of the top index. Okay. So initially, when our stack is empty, we start off with the top index pointing to 0. But then after that, when we push items on, we push it to where top index is pointing, and we increment top index by 1. So top index actually points to the index in our array, 1 above the actual item, the actual top item in our stack. So when top index is 1, that means there's one. So top index, you can also think of that as the number of items currently in the stack. So after we push one item on the stack, top index will be 1, and the actual item will be at index 0. So top index. So we'll subtract 1 from the top index to find the item, the top item, if we need to pop it, or we need to look at top and return that type item. Okay. So. So let's just look at our constructor and destructor here. So the constructor, the way I have it in our example code, you provide an initial allocation size. So you start off with a block of memory for your array. By default, if you don't specify this, it'll use 100. It'll allocate enough memory to hold 100 items. And again, we're doing this dynamically, and we're doing this template with a template class here. So whatever your type T is, using new, it'll allocate enough to hold 100 items, or you can specify an initial size if you want to. Okay. Although again, I should probably be a little bit more defensive here. as a precondition for this, initial Alex should be at least 1 or bigger. So if it's 0 or negative, my code would actually have a bug. It would actually break here. But anyway, I don't think I show examples of using this where you specify a different initial allocation size. So usually it'll be 100. So what will happen is we will create an array of items with enough space to hold 100, but there's no items on there initially. So initially the stack is empty. We indicate that by setting the top index to be 0 in this class here. Okay. And then our destructor, since we're doing dynamic memory allocation, whatever memory items is pointing to, if our stack goes away, if it goes out of scope, we want to delete those items. Okay, so we just call delete on our items pointer to be a good memory manager, to free it up if our stack goes out of scope. Okay. All right, so that makes most of our functions relatively easy. So clear is very simple, okay, because we're not assuming that we need to actually manage the memory of the objects that are on the stack. We assume that their memory is managed by something else, okay? So to actually clear our stack, if we have a bunch of items on our stack, all we have to do is set our top index back to 0, which is our indicator or our flag that there are 0 items on the stack and that everything is empty, okay? So now, even though we don't actually remove the items out of the stack, for example, if you put another item on the stack, it just overwrites the item that was currently on the stack at index 0, right? So there's no problem with that. So clearing out or emptying the stack is really simple for our array-based implementation. IsEmpty is a simple function. If top index is 0, then the stack is empty, so we just check whether top index is 0. This returns true if it's 0, and it returns false if it's 1 or bigger, which indicates that the stack is not empty. All right, so then let's look at push, top, and pop. So those are our main functions for a stack. And we need to push items onto a stack to actually use it. And we need to use top and pop to get them off and access the top items. So so for push, we're given a new item that we want to push on. Okay, so actually push is really not that complicated. I mean, all of this first bit that I have in the example implementation is all just dealing with what happens for our array-based implementation if our memory is full. So if for example, if our stack had enough memory to hold 100 items, once we push on 100 items, top index will be equal to 100. Okay, so at that point, our array would be full, and we have to allocate a new block of memory to hold our stack. And we need to copy all the items from the old block of memory to the new bigger block of memory that we allocate. So when the stack is full, when top index is equal to the alloc size, we double the current allocation size. So we set our new allocation size to be 2 times that. So basically, this is common for things that use fixed block size that need to grow in memory for you. So initially, it's 200. It's enough. It's big enough to hold 200 items of whatever your item type is. So it'll first double it's big enough to hold 100 items. So it'll first double to 200 items. Then if that gets filled up, it'll double to 400, then 800, and so on, right? So that's what happens here. So then what we do is we allocate a new block of memory of that new size. So we knew this will be 200, for example, twice as big as the old allocation size. And then we have to copy all the items. So this loop just copies all the items from the old block of memory to the new block of memory. Then once we've done that, we can safely delete. So we're no longer going to be using that old block of memory, so we delete it. And then we set up from that point on to be using this new items pointer as the actual block of memory that we refer to again. So besides that, which is just all dealing with checking and growing our array-based implementation if we need to, pushing an item on the stack is pretty simple. So just remember, top index points to the next empty item basically in the array. Okay, so you just assign the new item into what top index is pointing to, and then you just increment top index so it's now pointing to the next item above. Okay, so again, that has both the effect of keeping track of the size of the item. So again, if top index is 5, that means that we have 5 items on the stack, and they are in the array in indexes 0, 1, 2, 3, and 4. Alright. So again, because by now you should be used to using zero-based indexing for arrays, and that's why it works, that the top index is 1 greater than the actual index of our top item in our array here, in this array-based implementation. Okay. So, and then top is relatively simple, except in my implementation, I show we never talked about exceptions and throwing and caching exceptions in this class. You can go back and read the chapter, maybe skim over it, but yeah, I won't have questions on it. But here's an example of using exceptions. So exceptions are common in high-level object-oriented languages like C++ and Java. So at some point you ought to become familiar with them. So our textbook just actually halts the program if you try and look at the top item from an empty stack. I show a slightly different way of doing this. So we throw an exception. Okay. So if top index is 0, that means that the stack is empty. I could have also called the isEmpty function here as well, which might have been a little bit better. Reuse the isEmpty function. Right, so either way. So if it's empty, we throw an exception. And if you don't catch the exception, your program will halt, the same way that our textbook would cause the program to halt by just exiting, I think. Yeah, and only if it's not empty. So notice here we return the item on our array at top index -1. So again, to emphasize that, top index points to the next empty item in the array. So if I want the actual top item, I have to subtract 1 from that to access it. And so we just access that and return it there. All right. Okay, so I guess it's not isEmpty, it's isEmpty with a capital E, right? There we go. That should build. Alright, so yeah, that was top. And then pop, same structure, except instead of returning the top item, we're just going to remove it for the pop, alright? So pop doesn't return anything. It's just that if you're done using the item that's at the top of the stack, you need to get rid of it off the stack so that you can now start accessing the item under. So this is like actually taking the dish out of the cabinet, so that now you have a new dish at the top of your stack of dishes. Okay. So again, though, if the top index is 0, or equivalently, you could use the isEmpty member function. So if the stack is empty, we throw an exception. Otherwise, so notice here we don't actually delete. Again, we're not managing the objects in our that's in our stack in memory. We assume that those objects are created dynamically and then deleted by something else, the thing that's using our stack. We just decrement the top index. So now, even though the item is still in the array, we're no longer considering that as being on the stack anymore. So the item below that, top index -1, is now the actual top item on the stack. Now if we push an item, again, it will overwrite that bit of memory that was holding this item that we just popped off. Okay, so it's as if we get rid of it at that point. Okay, and then toString is not normally a function that's part of your abstract definition for the stack ADT, but I included it in my ADT. So you implement it so that we have a way of displaying our stacks to an output stream. Okay, and as I already showed, the overloaded output stream operator calls toString, and for for our array-based implementation of the stack, it goes through all the items in the items array and displays them. Okay. All right. So before we look at the list-based implementation, let's just show some examples of using my implementation, this example implementation of the stack here. So let's find main here. All right. So again, remember our abstract data type here is templatized. Okay. So all of these, we can have stacks of whatever type we want. So for my first one here, for using the concrete array-based implementation of stacks, we'll do an example for an array of strings. Okay. So again, notice I didn't specify the initial starting size. So, I could have said that I want an array that can hold 10 items initially, but since I didn't specify that, it'll give it 100 items as the size here. But I actually don't kind of really show that. You'd have to go back and look at that yourself to convince yourself that that's working here. But anyway, so as usual, a stack is a class. So when you make an instance object like this, you can call any of those member functions. So initially our stack should be empty. So yeah, if we call is empty, I mean the stacks always start off empty. At least in my implementation here. So some implementations you can give them some initial items to start with, but here you can't. There's no way to give stacks items. You have to push them on there to get some items into our stack initially. So anyway, it should be empty initially, which it is. So is empty returns a true result here. And here we're using our overloaded output stream operator. So we'll invoke the toString to show the contents of our stack. All right. So since there's nothing on there, it just I have an indication of the top and the bottom of the stack, but there's no items. So nothing. There's no actual items on there. So let's get some items on there. So let's push some items on. So remember now, since I'm pushing items to the top of the stack, the first item that you push onto a stack will end up at the bottom of the stack. So after doing these 3 pushes here, we should expect Derek at the bottom of the stack, followed by Susan, followed by Alan at the top of the stack. So a stack, I can't remember if our textbook talks about this, but a common thing is to describe a stack as first in, first out, or FIFO, right? So I'm sorry, is FILO. So FIFO is for queues, first in, last out. Okay, so here the first item in, Derek, is going to be the last item out if I start popping these items. Or you can also call this LIFO, last in, first out. So the last item in would be the first item out if I start popping things now. So since Alan was the last one, if we pop, it'll be the first one out now. So stacks are FILO or LIFO, whichever way you want to think of that. So yeah, now here we see our non-empty stack. If we display it, like I said, Derek is at the bottom, followed by Susan, got pushed on, followed by Alan is our item pushed last and is at the top of the stack, right? Okay, and we can get the top item. Now, top item, again, doesn't remove the item from the stack. It just kind of peeks at it so you can see it or use the top item. So the top item, this return from top, is Alan currently for this version, for the stack at this state right now. And the stack should no longer be empty. So if you look at is empty, you get false there. All right, and let's pop some items off of there. So again, notice popping items and looking at the top item are separate. So if I pop the items, I just lose them, so I don't get a chance to use them. So if I wanted to use the current top item, I'd have to use the top here and do something with it. If I want to just get rid of the top 2 items, to tell you the truth, it's really not normal to do something like this, to just pop. What you normally do is something like this, and I should have maybe shown this in the code here. So normally when you want to use the top item, so since this is a stack of strings, I can create a variable called next item. So normally what you do is you save, you squirrel away the value that's returned from pop. And then I can do something with that. So here I'll just do something with it by just displaying it, for example. Okay, so this is more typical of how you use pop. You pop off that item into a variable, there we go. Sorry, into a variable, and then you do something with it. I'm just displaying it here, but you could use that for a calculation or whatever. Okay? So I'm going to try to make one more video where I actually do some examples of using stacks to do things. You know, like the infix notation example from our textbook or something like that. So if we run that, oops, got some build errors here. Oh, I'm sorry. I had that reversed, didn't I? So I was getting confused between my top and pop. So what I meant to say was the normal way to use top is to take the top item. So because pop doesn't return anything. Sorry about that. So it is usual to use pop just like that, since it's not popping anything. It's not from next item, it's from the stack. So this is kind of the common way you use top and pop. So you look at the top item and do something with it, and then you pop it off when you're done using it. Right? So yeah, I'll get the top item, do something with it, and pop it off. Anyway, there, back to building correctly. So that was the example that I just wrote here of using kind of top and pop in combination. We took the top item off, saved it in a variable, displayed that, and then once we're done using it, we pop it off. Okay? But anyway, to continue on, so I popped off a second value from the stack, right? So now, I've popped off the two top items, so I should only have one item on my stack here now, right? So yeah, when we display it, we see, indeed, there's only one item, and it is that item there on top here. All right, and then finally, as I discussed a bit, there's different ways that different stack implementations handle popping or doing top from an empty stack, right? So in actuality, the standard template library doesn't warn you. Your program just crashes, right? Which is kind of, to me, it doesn't even throw an exception, which is a little bit strange. So, but anyway, so I think like Java, for example, throws exceptions when you try to do things like this from an empty stack. So in my implementation, we actually throw an exception here. So if we pop off this last item, our stack is now going to be empty, right? So now, after I did this pop, our stack is now empty. If we display it, there's nothing on there. So now if we try to do top, you'll see that an exception is actually thrown. If I didn't catch this, my program would exit at this point with a message about uncaught exception, with an uncaught caught empty stack exception, right? But here we've got a try catch block, so we're actually catching that exception. Instead of exiting immediately, then we display a message that we caught that empty stack exception here. So, all right. Then the same thing happens for pop. If you try to pop from in this example implementation of our stack data type, so it throws an empty stack exception. All right. Okay, let me pause for a second. I'll be right back, and then we'll look at the list implementation. Okay, and let's look at our list-based implementation. So we're going to be using a linked list, like we talked about in the previous unit in this class. So let's see here. So there's these are all our array stack here. Oh, there it is. Sorry. So so for our linked list based implementation, so this has some advantages. We talked about these when we talked about linked lists. So to use a linked list for a stack, again, it's relatively straightforward, right? And it has the advantage that you don't have to worry about that memory size getting full. Okay, so like our textbook, the way our textbook did it is that you had to say up front what the maximum size was, and then if your stack grew too big to fit in that size, that was it. You just couldn't use that stack anymore. You just have to create a new stack of bigger size, right? So that's typical in some implementation. So it's just you have to state up front the maximum size that your stack can grow to. Okay. So the way that I did it here makes it gets rid of a little bit of that inconvenience, but it does still have the disadvantage. So if your stack does grow, if your array-based stack does grow too big to fit in there, I mean it could be really expensive to expand that memory and copy over all those items. So you might all of a sudden, your program might grind to a halt if you just unexpectedly get your stack a little bit too big doing that kind of thing, depending on how long it takes to copy items like that. So a linked list based implementation would avoid that. But we are, every time we're adding a new item to a linked list based implementation of a stack, we're going to dynamically create just a small bit of memory, just big enough to hold the item and then to hold a pointer, so we can link these together like we did for a linked list. All right, so let's just jump into the implementation. So if you look at the declaration for my L stack, the linked list version of the stack, it looks almost exact. It does look exactly the same as the A list implementation, because we're basically going to make concrete implementations of all of the abstract member functions that define our abstract stack data type, right? Plus we have the same constructor. The only difference is our constructor, we don't have to specify like an initial size because for a linked list based implementation, it doesn't make sense, right? It will always dynamically grow whenever it needs to when you add new items on. And also in this case, it will also dynamically shrink. So you will really only be using exactly as much memory as you need at any given time to hold the items on the stack in the linked list implementation. Exactly as much, except as we talked about, there's a little extra overhead. Every node needs a little bit extra to hold the pointer, so that you can link these up into your linked list. So there's that's a disadvantage of linked list. There's that overhead. All right, so constructor is simple. I should have mentioned so we've only got one private variable. So like for our linked list that we talked about before, we don't keep track of the tail of the linked list. We only need a pointer to the top item of our linked list because for a stack we only access items at the top, all right? So next week when we talk about queues and we do a linked list implementation, we'll need both a head and a tail pointer because you need to access items at both ends for a queue. But for a stack, you only add and remove things on at the top, so we just need one pointer, the one pointing to the top item in our stack, all right? When the stack is empty, when there's no items on the stack, we indicate that by using a null pointer. So when stack top is null, that's an indication of an empty stack. All right. When our stack, a linked list implementation of our stack, when it destructs. So remember, we're going to have a bunch of dynamically allocated nodes, possibly. So if we have a bunch of items on our stack, we've got all these nodes linked together. So again, to be good memory managers, we want to delete those. We want to free all those up before our stack goes away, okay? And we do that, so we do that with the clear function. So the clear function does the same thing. Remember, clear is supposed to empty out the stack. So for our linked list-based implementation, unlike for the array-based implementation, we need to dynamically deallocate all that memory, so all those nodes. We can't really reuse the nodes in our stack here. So we need to delete all those. So clear, to empty out our stack, basically it iterates through the current linked list of nodes, and it deletes all of them, okay, with kind of the complications that we talked a little bit last time when we talked about linked lists, that you have to be careful not to lose track of your node. So we first save the current top into a temp variable. That way we can safely increment our top to the next node in our linked list. But since we've remembered that, then we can now call delete to free up its memory. We keep doing that till we get down to the end of our list, which the last item should have a null pointer from its link. So that'll be how we know that we've gone all the way through our linked list and freed everything up. So again, since we're using null for stack top to indicate an empty stack, we can just check that for our isEmpty function. And then that finally gets us to our push, pop, and top functions, kind of the heart or the meat of our stack class. So, when you push an item, basically you have to first start off by dynamically creating a new node to hold the item. And then you initialize the item for that new node, for that item that was pushed onto the stack. And then we just, since now this new node is going to be the new top of the stack, you have it link, so you have its link point to what the old stack top was, and now the new stack top becomes this new node that we just created, okay? So again, if you don't quite follow that, draw a diagram and convince yourself that works to push a new item. And this also works if the stack is empty. So if the stack is empty, stack top will be null, and what you'll do is the new node, you'll set its link to null, indicating it's the last node on your linked list, and then you'll set stack top to be to this new first item that you push onto the list. So it works both for an empty stack or for a non-empty stack, where stack top is actually pointing to the top item on our linked list. So top and pop then are relatively simple. So for top, again, we do the same check that I did for the array-based implementation. It's undefined of what happens when your stack is empty to do top on it. So we throw an exception in this example implementation of a stack that I gave you. But otherwise, all you have to do is access stack top is pointing to the top item. So whatever so it's pointing to the top node. So whatever item is in their top node is the item that's at the top of the stack. So you can just take that and return it. That's it. Okay, and then to pop, a little bit more complicated. So again, if it's empty, we throw an exception. Otherwise, we want to, it's a little bit more complicated just because, again, we want to delete that node. So we're no longer using that top node that we're now popping off. So we temporarily remember what the current top is. So we do the actual pop by following the link. So now after doing this, stack top is pointing to the one that was below the top node. That becomes our new top node, or the new top of the stack. After we've done that, now we can safely delete the old top, which temp is pointing to, and get rid of it. And then our two-string implementation. So instead of going through the items of our array, we have to follow the pointers in our linked list to find the items in order on our stack. But that's what the two-string implementation does. Let's go down here. Let's get rid of these breakpoints. I mean, in actuality, though, what you'll see. So again, remember to bring it back to the talk about what an abstract data type is. So what you'll see is that the way you use, whether you want to use an array-based implementation, like I did before, or you want to use a list-based implementation, so use an LStack. So it doesn't really matter to you using these. You use them in exactly the same way. Okay, so my second example of using LStack, which is using a concrete list-based implementation of the stack, does exactly the same operations as before. Pushes, pops, checks is empty, right? It's just that behind the scenes, our concrete implementation is using a linked list instead of an array. But the way you use it, the abstraction for a stack, so for both of these concrete implementations, they implement the same abstraction. They implement the same operations, push and pop, and is empty, and so on, that you can do on the stack. Okay, that's what an abstract data type is. Okay, your concrete implementations, it doesn't matter the details. They might implement them differently, but they provide the same interface or the same way of using a stack in this case. All right. So I won't spend as much detail looking at this since it's really the same way of using these. So you can use is empty. You can use push and pop. So initially, our list-based implementation of our stack is empty. Oh, I should have mentioned again, since our stack data type is templatized. On the second one, instead of using strings, I show a stack of doubles in this case. So we create a linked list stack of doubles here. So we can check if it's empty. We can call toString to display the contents of it. We can push some items on there and display it. So now we've got 3 floating point values, 4.2 raised to the 10 to the 43 power, and then -3 to the -15, and so on. That was the 3 floating point values that I popped on there. So again, they should be in reverse order. So this last one, 42e to the 42, or 4.2e to the 43, should be the one that's on top, and 4.2 should be at the bottom here. Okay? And so on. So and we can pop our 2 items off. Now we've only got 4.2 on there. And if we try to pop from if we try and look at top from an empty stack in this implementation, it throws an exception that we can catch, that kind of thing. All right. Okay. So yeah, in summary, we covered those things. There were really kind of 2 things that we talked about here, Dave. I mean, we talked about stacks in particular. So the abstractions of a stack, the idea. That what a stack does is you can push and pop things onto it, and you can look at the top item and do things with them. So in the next video, we'll look at what uses you can put stacks to. So actually doing things with stacks. All right. The other kind of goal, the other thing that we did in this video, though, we learned a little bit more about what we mean by an abstract data type. Okay. So we saw the abstraction of a stack, the base class that we had, and then we made 2 concrete implementations, an array-based implementation and a linked list implementation. Okay, but if you want to use these, you really don't care which one it is, except that you might care about the performance implications of using the different type of implementations. So, okay, anyway, that's it for this video. Hopefully that's helpful, and I will see you in the next video.